So, welcome to module 5.2. In this we will understand the working of the assembler, right. So, let us now start with, so this is the input to your assembler, this is the mnemonics. Now, we have to convert this mnemonics into the 16-bit series of 16-bit instruction, and as you see there are 19 instructions, 20 instructions here, and we have to convert each one into its equivalent 16-bit part. Now, these instructions are going to be in the memory, in the instruction memory, the ROM 32K, and the data that it is going to use. What are the data here? For example, I is a data, sum is another data, at least two data points that we are seeing. I and sum are basically going to be in the data memory, right. So, so when the assembler is assembling, it should also assign some memory location for I and sum in the data memory, right. So, the role of the assembler is also allocating memory for I and sum in the data memory, right. Now, let us just look at this. Understanding of the C type instruction is very straightforward, right, but understanding of the A type instruction, there are some things that we need to note here. Let us first look at the A type instruction at. After at, you can have a constant. For example, I have at 100 as you see here, right, or after at I could have a variable as you see at I here, at sum here, at end here, right, at loop here. Sorry. So, I and so there is a difference between at I, at sum, at end and at loop. The difference is very simple. I and sum are basically data, while loop and end are basically symbols or labels used in instruction. What do you mean by used in instruction memory? They are used to designate locations in the instruction memory. If I say jump to loop, where is that address? Jump to which address? Jump to an address within the instruction memory. So, at instruction itself, we need to distinguish three things: whether what is going to follow that is a constant, right, it should be a decimal constant, it is a non-negative decimal constant, or we should, is it a symbol which is, it will be a label symbol. This can point to data, this can also point to a label like loop and end, which will be pointing to some location in the instruction memory. In addition, you will have comments, and these comments have to be ignored, right. So, one of the basic step that is involved in assembly is to first resolve these labels. Finally, when I translate to binary, every one of this at instruction will have a value, right. We do not have I in the binary representation. I need to replace I, sum, loop, end, all these things with a 15-bit binary value, and that is very, very important here, right. So, so the assembler will first to go through this program once, that is called a pass. It will pass through this program once, that is, and then it will pass through second time. So, the assemblers, the traditional, even for the major systems, the assemblers are 2-pass assemblers. What do you mean by 2-pass assemblers? The assembler will look at the program twice, it will read the program twice. in the first pass it will resolve all the symbols. So, the first pass it will resolve all the symbols. What do you mean by resolving symbol? For every symbol that is following an at instruction here, I need to replace it with a 15-bit binary. So, I should, that means I need to have a value, a constant value assigned to every such labels that is following an at instruction. For example, I, sum, end, loop, all these things you are seeing in this particular code, I need to replace it with a constant. Then only I can convert it into the corresponding A instruction, right. So, the first pass of the assembler is basically to resolve these symbols, basically replace these symbols with constant values, so that in the second pass it basically generates the binary. There is no problem for us, we have understood how to convert m equal to 1 as you see here the second instruction or any of these C instructions, how it is converting into the binary, there is no issue. The A instruction, this is the issue, we need to resolve the symbols, we call it a symbol resolution. To do the symbol resolution, we basically have something called a symbol table. So, when in the first pass, when the assembler is going through the first pass, it creates something called a symbol table, and in that symbol table, what is that symbol table? It is very simple. For every symbol that I am using, its equivalent constant that I need to replace will be there in the symbol table. So, the symbol table will map every symbol in your program, in your mnemonic program into its corresponding value, right. So, the pass 1 of the assembler is basically to construct this symbol table, right. Now, let us see, so let us see how it is going to do that. Now, the first one is a comment. So, your first line is a comment, you have to ignore, nothing there. So, a comment does not become binary. The second one is at A instruction. So, you have a counter which says, so this A instruction, so you should maintain a counter here, the counter currently is 0. This means this A instruction, the equivalent of this A instruction will be in the ROM, that is the instruction memory location 0, right. At this point you have found a symbol I, so you register that symbol I in the symbol table. You do not know what that I is, but you just register. This I can be a label, this I can be a label like loop, right, we do not know what is I. So, register I. Now, go to the next instruction. Now, this is not an at instruction, this is a C instruction. So, just make it 1. I am now describing the pass 1 of the assembler, the first pass. Okay. Now, I come to the third instruction, that is 2. I see another symbol here, I register that symbol sum in the table. Okay. Now, I see that fourth instruction here. Now, I see a loop, a symbol loop. Okay. This is a symbol, right. So, the loop is registered into a symbol table, and this is pointing to the fifth instruction, or what, sorry, this is 3, this is pointing to the fourth instruction. So, if I say at loop means I have to jump to the fourth location in the ROM. So, when the moment I see a symbol that is with the parenthesis here, this is a label here, the moment I see a label, I just, the counter here is 3, I put the next 3 plus 1 4 here. So, loop becomes 4. Then next is an at I instruction. So, I go to this I see this I go to the table and see if I is already registered. I need not register again. So, that is one very important thing. When we are populating the symbol table, we are just building the symbol table. Every time a new entry has to be entered, we should check whether it is already registered. I is already registered, so nothing to do here. We make it 4, counter becomes 4. So, for the symbol there is no equivalent binary. So, right. So, we just, this is not counted. So, I come to I and I make it 4. Now, d equal to m, this is 5. Now, at 100 is a constant. So, nothing to do, this becomes 6. D equal to d minus a is 7 at end. So, we enter end here, and this is going to be your 8th instruction, then this is your 9th, we are just counting this. At I, this is your 10th, I is already registered, so nothing, then this is 11, at sum is 12, sum is already registered, nothing to do, this is 13, this is 14, this is 15, again I is already registered here, so nothing to do. At loop, again loop is already registered here, nothing to do. Now 0 colon jump, this is nothing to do. Now end is a symbol. So end points to the 18th instruction in your RAM, 17 plus 1. Now I go and see if end is registered, yes, end is already registered. So now I update that value to 18. And this is 19. Now, after you complete the program, whatever, these are the symbols and these are the values, the second thing is the values. For whatever symbols the values are already populated, they are all labels in the program. For example, loop and end, as you see here, are labels in the program, and those values. The remaining thing, whatever is not populated, they correspond to data. So, I and sum are data. Okay. So, I now make, say, so I and sum, they are in the data memory. So, I can make I as 0 and sum as 1. So, I will be in 0th location in the data memory, sum will be mapped onto the first location in data memory. Let us understand this. Now, what has happened as a part of your first pass? All the symbols have been resolved, and we had clearly made a distinction between whether it is a label of the program inside the instruction memory or it is a data pointing to some variables in the data memory. In this case, loop and end are basically symbols in the program. So, they get 4 and 18 as you see here, while I and sum are basically data in the data memory, and then for that we assign 0 and 1. So, now now we can just see that this is going to be at 0, this is going to be at 1, and this is at 100, this is going to be at 18, and this is going to be at 4, and this is going to be at 18, right. Now the program works. So, at loop is nothing but at 4, I jump to the 4th instruction. At I is, I access I which is at 0, which is equivalent to at 0. At 0 is in data memory. At 1, similarly at end, when I jump on greater than, I jump to at 18, at 18 is this, and I do a unconditional jump again back to 18, it is at 18. So here, so essentially we have actually resolved all the symbols, and this is precisely what your pass 1 of the assembler has to do. So what it means to do, so let me just sum up some of the important points here. First thing is, we have a running counter. That counter will ignore all the comments, like it has ignored add, and ignore all the lines which basically has only the symbol, like loop had only a symbol, end had only a symbol, etc. And then for every instruction that it sees, a C instruction or A instruction, it increments. So it starts with 0. So ultimately this counter tells for every instruction which memory location in the instruction memory it is going to be loaded. For example, at I will be loaded at 0. This m equal to m plus 1 that you see here is going to be loaded at 15, right. So like that, right. And when we are doing this part, whenever we see an at instruction, and if there is a constant we do nothing, if there is a variable then you go to the symbol table and see if that variable is already registered. If the variable is registered, do nothing. If the variable is not registered, then you make an entry. This is what we do at the at instruction. So what we do at the at instruction, if variable, first if variable is there, check for entry in symbol table. Yes means do nothing, no means make an entry. Okay. Yes means do nothing, no means make an entry, right. And this is what you do for every at instruction. And whenever you see a symbol, symbol is with parenthesis loop. Whatever there is a counter, whatever the current counter plus 1, right. Whenever you see a symbol, first go to the symbol table and find out if the symbol table is registered, if the symbol is registered. If it is registered, fine. If it is not registered, register it. In addition, also whatever the current counter, that plus 1 you put in the value of that symbol, right. So first time we saw loop was not registered in the symbol table, the loop that you see here, I am marking it here. That loop was not registered in the symbol table, so I go and register that in the symbol table as you see here. Loop is registered, and also we entered that counter, the counter was 3 when we encountered loop. So we basically 3 plus 1 4 is put here. So loop, the moment I touch, when I see loop I put 4. So whenever I see a symbol which is within 2 parentheses, a label, we will call it label henceforth, I see whether that label is already registered. If it is not registered, you register it in the symbol table, and also along with it associate the value which is the counter plus 1, right, and that is what we do. So this is the thing. So we are interested only, we are in the pass 1 we have to have the counter running, and every time I encounter an at instruction or a symbol, a label, I now start going and accessing the symbol table and do the actions as I had mentioned. At the end of this complete one pass, after you finish, say in this case all the 19, 20 instructions, then you go and see what are all the symbols in the symbol table where the values are already finalized. In this case you will find that I am again going back to the symbol table, I will find that this 4 and 18 are already finalized. For those for which the symbols are already finalized, they are actually labels in the program, obviously, right. And for the remaining thing for which the values are not finalized, in this case I and sum, you just put a, sequentially assign them starting from 0 in this case. So, I will assign I as 0 and sum as 1, and if you do that, then essentially the resolution of the symbol is over. Once I have that resolution of the symbol done, now it is now a more straightforward conversion for me during the phase 2 or the pass 2 of your assembler. So, this is pass 1 of the assembler. Now, the only change, practical change between what we have seen here and the real construction that we will be doing as a part of your project 6 is that there are some predefined symbols, like you have been using at screen, at keyboard, etc., right. We had seen in the previous case. So, like that there are lot of predefined symbols that will be used actually by your virtual machine later. So, as of now there are certain predefined symbols. An example of a predefined symbol is your screen and keyboard. So, when you initialize your symbol table, please note that this is also there in the book. When you initialize the symbol table, right, the symbol table will have these entries already. For example, it will have SP, which basically stack pointer. We will see what a stack pointer is later, right. LCL, local, right, arg, argument. So, SP, LCL, arg, this, that, we will see what is this, what is that later. Then you will have 16 symbols R0, R1, R2, R3 till R15, then screen and keyboard. These are all what we call as reserved symbols. We cannot use this symbol in our program. For example, in our previous thing, I could not say that this is at R0 or at screen, I can't say at screen and have my own variable, right. So, these are all reserved things. So, I can't use in lieu of I any of these symbols, right. So, these are all reserved symbols. So, SP, local, this thing. So, in your data memory R0 to R15 are reserved, that is 0 to 15 are reserved. So, in a data memory what will stay is R0, R1 to R15 will stay in the data memory first. So, the first 16 locations of your data memory is reserved for R0 to R15. Okay. So, that means that your I and sum cannot be in your 0 and 1 location, your I and sum will start from the 16th and 17th location. So, the only change between the explanation I gave earlier and this is that after you finish your one pass, you will go and find out what are the symbols that are already resolved, like loop and end, that are 4 and 18, there is no change about it. Then there will be some symbols which are not resolved, those are variables in the program in this case. What I told earlier was you start numbering them from 0 onwards, instead of doing from 0 onwards, do from 16 onwards. So, 16 and 17, right. So, essentially your symbol table will have I, sum, loop, end, which is 16, 17, 4 and 18, and that in addition to this SP2 this. So, there is one entry, second entry, third entry, fourth entry, fifth entry, there are 16 entries here. So, which will be to 21, 22, 23. So, 23 entries are always there by default when you create the symbol table. In addition, for this particular program you would have created 4 entries which will be beyond this. So, I is 16, sum is 17, then loop and end or 4 and 18 or whatever, okay, 4 and 18. So, this totally the symbol table now will become 27 entries, right. So, this is what you do in pass 1 where we resolve symbols. Sorry. Now, in the pass 2 what we do, every symbol is resolved. So, we just have to now convert this each instruction into its corresponding binary. So, 20 binary instructions will be 20 binary instructions will be created as a when we by the assembler when we take this. So, predominantly the assembler has 3 modules. One is the symbol table module, which will be used in pass 1, which will be the symbol table will be constructed in pass 1 and it will be used in pass 2. In the pass 2 where do you use the symbol table? Whenever I see at I will go now to the symbol table to find out what is I. At sum I will go to find out what is sum. Similarly at I, at sum, at loop, at end. Whenever I see an at instruction and a symbol, I will go and find out what is that, right. The other things I just have to ignore. So, the symbol table is used in the pass 2. So, this symbol table so there are 3 modules as I have noted here. The symbol table, which will be that module will be used to construct during pass 1 and that module will be queried in pass 2 when we are generating the binary. Then there is a parser. What will this parser do? It will basically read line by line and make a decision of what we need to do. For example, the parser in this case will read line by line. The first line it will read, oh, it is a comment. The second line it will see, oh, it is an at instruction, and then what is it, right. And then, oh, the third instruction is m equal to 1 followed by a comment here. So, this comment I have to ignore, I know what is m equal to 1. Then similarly at sum, at m equal to 0, loop, at I, all these things it basically loop. Here in the pass 2 the parser need not do anything. In the pass 1 it should say it is a symbol, it is a label, then only have to go to the symbol table and do. So, like that the parser basically is very much responsible for doing identifying the different components. So, to sum up, the parser actually makes a distinction between whether it is an A type or a C type or a label, and then based on that we can take necessary action. The last module that we see is the code here. The code will basically take the parsed instruction and generate its equivalent 16-bit code. The code will be used for this. So, these are the 3 important modules that we need to generate as part of our assembler construction of this assembler, right. Ultimately, we need to generate a program called MyAssembler. To this MyAssembler, I will give you the program.asm and we need to get, and this MyAssembler should generate the program.hack, which is nothing but take all the instructions in your program.asm, ditch all the comments and give a 16-bit equivalent of that, which I can take it forward and run it on my binary, run it on my hack hardware that we have taken. So, this is basically the 2-pass assembler and understanding of the 2-pass assembler. So, next module we will now go and talk about some of the simple but vital things of how to make this software, the assembler software. So, how do you, this will give you an introduction of how to develop software, how to develop what we call as APIs, application programming interfaces. So, this will be a good introduction to systems programming, which is a very, very important part. Today, one of the major talent that we need, that our country has needs here, is system architects, people who can actually understand operating system, people who can actually understand compilers. There is a very big need for that type of a talent, and I am sure when we start writing this assembler, when we go deep into how to write the software for that assembler, we will understand many things which in a long run will be extremely beneficial to us. So, we will move to the next module. Thank you.